Hey class, and welcome back to the third part of chapter 14, where we're now going to look at fluids in motion. Yay! My wife says she loves fluids in motion. Um, she must be thirsty. Anyway, sorry. Okay, so what makes fluids move? Well, what makes fluids move is actually a pressure difference. All right? Pressure difference accounts for so many different things with fluids. Why is there buoyancy force? Pressure difference above and below, right? Why do fluids move? Pressure difference. Things will always want to accelerate from low pressure to high pressure. Why? Because pressure difference, pressure is force over area, means a force difference. Difference in force means acceleration because of Newton's second law of motion. So when you have a fluid that's moving, there's actually a couple different factors that we need to consider, and we're going to talk about those now. So first of all, the style of flow, or the manner in which the fluid is flowing, you need to consider. There's two kind of options you have. First of all is what's known as steady flow, when all the particles are sort of moving together in unison, closely at similar speeds to the particles around them. All right. The other is unsteady flow, which means the velocity of the relative particles are not the same. So you can have different amounts of chaotic flow between different particles at different points. And when you have an extreme amount of difference in velocity, direction, and magnitude of different particles within a fluid, you call that turbulent flow. So very steady flow we'll call laminar, and very unsteady flow we're going to call turbulent flow. To help you visualize what this looks like, here's a couple images. Here you see laminar flow. Things are all moving in the same direction. So the direction of the velocity vectors are all the same, and there's magnitudes are really quite similar to one another. And here's kind of an extreme case of turbulent flow. Here you see flow around maybe a baseball moving through the air. So it's laminar in front and on the sides of the object, but you get turbulent flow, more chaotic flow behind that object. Here's an airplane wing where you see nice laminar flow in front and turbulent flow behind. If this turbulent flow region becomes too large on top of the wing, that's where you feel what we call turbulence in an airplane, which is usually a loss of lift and makes your airplane feel like it's dropping. All right, so that's steady versus unsteady flow, or laminar versus turbulent flow. Another thing I want to talk about is what's known as viscosity. So this slide here kind of shows sort of the technical definition of viscosity. We're not going to get into a lot of this in detail in this class. You'll see it in future classes in fluids and so on. But I just want you to understand what viscosity is it's really just a measurement of how resistant a flow or a fluid is to flow. So something with high viscosity might be something like honey, where there's a lot of viscous forces or almost internal friction within the fluid that makes it less likely to flow rapidly. Something like water or oil has very low viscosity and as a result has low internal friction resisting its flow, and so it's able to flow very rapidly. Okay, so again, viscosity is really a way of measuring how much resistance there is to flow within a fluid. And so something that flows very fast and easy and rapidly, low viscosity. Something that's highly resistant like honey or ketchup would be high viscosity. So here's some examples of different viscosities. Air is extremely low. Water is very low as well. And then things like shampoo, honey, and then glass. Old glass is actually a liquid that flows. In old cathedrals and things in Europe, you can look at them and the glass at the bottom is actually thicker than it is at the top, not because they are made poorly, but because that glass has actually flowed over time, but it has an extremely, extremely high viscosity, so it flows extremely, extremely slow. So, a couple other characteristics of fluid that are particularly important to consider when they're in motion. One is what we would call either a fluid as being compressible or incompressible. Well, what does that mean? Well, let's take, for example, this room, okay? In this room, it's full of air right now. I could take all the air in the room that I'm in, and I could shove it into probably a single scuba tank. So air is highly compressible. I can take a large volume of it and shove it into a much smaller volume, and it would still be possible, or is able to do that. It's able to be compressed. If I have this room full of water, and a snorkel, I guess. If I had this room full of water, I could fit it into an object about the size of this room. Most liquids, like water, are highly incompressible. You can't force them into a smaller volume. Okay, so that's what compressibility is. Fluids can either be viscous or non-viscous. Now, in reality, all fluids have some magnitude of viscosity to them, some resistance to flow, but an approximation we can make for things like water and oil and air is that they're approximately non-viscous. Those forces within them resisting the flow are so small that you can ignore them. But when you're dealing with something like honey, again, or thicker oils and different things, you cannot ignore that any longer. So if you have a fluid that is incompressible, non-viscous, and undergoing steady flow, so it's not rotating or anything relative to the parts around it, if you have all of this stuff going on, then you can assume or call it an ideal fluid. So we're going to make some assumptions now and look just at ideal fluids. And then again, when you continue your education and have a few more tools in your tool belt, you can consider situations where you have non-ideal fluids. But we're going to talk about ideal fluids for now. The primary example we'll use is water and water-like substances because they are nearly non-viscous, highly incompressible, and you can create situations where they're undergoing steady flow. Okay, so we're going to just assume ideal fluids for now in the future examples. So if you have an ideal fluid undergoing steady flow, it will follow what's known as a streamline anytime it's moving. And so you'll see examples of streamlines, or you probably even heard the term of having a more streamlined aerodynamics. So if you have, for example, this guy on a bike here, you have more streamlined flow as air flows around him because of the shape of his helmet and the position that he's in. You get a more steady flow going around him. Here's flow lines around a bullet moving through the air. As you can see, there's turbulence behind it and more steady flow around it, with the streamlines being followed up here but not behind it. And then here's a car with some computational fluid dynamics done, looking at the way air is flowing around it and its airfoil, trying to minimize the amount of turbulence behind the vehicle, because this turbulence behind, as we mentioned back in chapter 6, gives rise to air resistance. So just so you understand, here's what water flowing through a pipe would look like if you're assuming ideal flow, and here's what a fluid moving through a pipe would look like if you're assuming viscous flow, because viscous flow means friction, and so at the outer edge, friction is slowing down your fluid, and it's only in the middle that it's moving at a high speed, whereas if you assume ideal flow, you can assume it's moving at the same speed at all points. All right, so the next thing I want to talk about is mass flow rate. All right, so if we think about fluid moving through a pipe, all right, if you're looking at some point, let's say over here at point 1, you have some chunk of water that's going to move through it in a given period of time. How much water moves through it in a given period of time? Well, that's going to depend on the density of the fluid, the area of the pipe there, and how fast the fluid is moving. But what we have found and proven, especially with an ideal fluid like water, is that when you have an object or water moving through some object like this pipe, you're going to have the same mass of water moving through this point as you do over here at this point in a given period of time. Why is that? Well, if you don't, this water is either going to run into this location, increase the pressure and make it go faster, or if this one's moving too fast, it will create a vacuum behind it, an empty void, which will then pull backwards on it, slowing this one down and causing this one to accelerate. And so because of it being a closed system, you'll have a more or less constant mass flow rate all the time. And the way that we quantify mass flow rate, as you see up here, change in mass is just pressure times change in volume, right? Volume is just going to be your area, your cross-sectional area, multiplied by x, the horizontal distance. And the horizontal distance is just your velocity multiplied by your change in time, all of which you see right here. And so if you divide both sides by time, you get the mass flow rate as being equal to the density times area times volume. And so what the equation of continuity tells us is that the mass flow rate is the same at every point in an enclosed tube, provided you have steady flow. So if you have steady flow, then the mass flow rate is going to be the same at all points in your pipe. Regardless of the diameter, regardless of the speed of the fluid, you'll have the same mass flow rate at all points. And so this enables you then, if you know information at one point, to calculate what's going on at some other point in your pipe. Pretty cool. So again, just so you understand, this is for steady flow here. If you have an ideal fluid, what does that mean? Ideal fluid means that your density will be the same at both locations because it's incompressible. So for an ideal fluid, that's reduced to just A1V1 equals A2V2. And just so you're aware, when you have area times velocity, this V, lowercase v is velocity, not to be confused with the capital V of volume. All right, this lowercase v of velocity, this gives you your volumetric flow rate because you have the units here are cubic meters per second. So here's just a fun example for you. Say you're filling up a bucket with a hose, right? You're leaving it unobstructed and you're letting the bucket fill up and you're letting the bucket fill up and it seems like it's taking forever. So you decide to cover the hose by putting your thumb over the top to make it shoot out faster. Okay? I got a couple questions for you about this. First of all, I'll give you some information. Here's the cross-sectional area of the hose when it's unobstructed. The volume of the bucket you're filling up is 8 times 10 to the negative third cubic meters. And when it's unobstructed, you could fill it in 30 seconds. Okay? So I want you to tell me, first of all, what is the speed of the water leaving the hose when you don't obstruct it? And then if you were to obstruct it by covering it by half, how fast is the water going to be coming out? And then the last question is that going to make it fill up any faster? So, first question is to find the speed. All right, so speed is just volumetric flow rate over the area. Volumetric flow rate is volume divided by time, and the area was already given to us in the problem statement. So our volume, 8 times 10 to the negative third meters cubed, divided by the 30 seconds, and then divided by the area, we find, boom, that we get a box-worthy speed of 0.936 meters per second. Then for part B, we're asked to find the new speed when you cover it up halfway. Well, it's an ideal fluid, right? It's an ideal fluid, so we can use this reduced equation of the continuity equation, and solving for V2, what you find is that the speed just ends up doubling to 1.87 meters per second. So the question is, will you now be able to fill up the water bucket faster? And your answer is no. The water comes out faster, but the quantity of water comes out the same. It'll still take you the same amount of time, provided you have an ideal fluid. And in reality, if it's not ideal, you'll probably get some turbulence here, so it will actually take longer. So don't cover it up to make it fill up faster. It won't help. All right, so now I want to introduce what's known as Bernoullis equation. It's really quite a fascinating equation, and it has a lot of really neat applications. So when we talked about the equation of continuity, that was all fun and good, but that only applied to things at the same elevation. What happens if you have a change in elevation in your fluid? Well, if there's a change in elevation, you're going to have a drop in pressure as a result of that change in elevation from what we learned in video 1, right? So let's look at some of the forces once again. Some of the forces, the net force acting on a fluid, as you recall, is going to be the pressure multiplied by the area. So now I want to look at work. If you remember, work is force times distance, right? Net force times the displacement of your object is the work being done on that object. So now let's look at the work being done on a fluid. If force is pressure times area, then work is pressure times area times displacement. Area times the displacement is just the volume of water moving through your pipe. And so what we find is that the net work being done on a fluid is just going to be equal to the change in pressure multiplied by the volume of water moving through your system. So we can set that equal to, then, what we already know about energy, right? This work is going to be equal to our change in energy. The energy we start with minus the energy that we end up with. And so continuing to move on, let's get rid of this volume because we don't want to have to worry about the volume of water. So if we divide through by volume, It gets rid of the volume at this point, and then we have mass over volume in each of these terms. Mass over volume is just density of your fluid, and what we get is what's known as Bernoullis Equation, which is really just conservation of energy 3.0. It's our third conception of conservation of energy, and what it tells us is if you have a steady ideal fluid, so a steady, non-viscous, incompressible fluid, you can quantify the pressure, speed, or height at any different point by using conservation of energy in a new form of really just looking at work energy per unit volume. So pressure divided by volume gives you, work divided by volume gives you pressure. And so then dividing all of your energy terms by volume gives you this new conception of energy per unit volume, which is known as Bernoullis equation. So if you look at this, again, keep in mind, this looks just like our old energy equations, only now instead of work, we have pressure. So keep that in mind, right? So thinking about Bernoullis principle, I want you to think for a minute about this example problem. I don't know if you've ever seen this, but imagine you have a truck, all right? And if you have this truck that has a tarp over the back, maybe it has, let's say onions in it. I don't know why I've seen an onion truck like this before. So it's got a bunch of onions and obviously some empty airspace in it, and then it has a tarp over it. It's stopped at a stoplight and the tarp is flat. Once it gets moving fast, what happens to the tarp? It actually bulges upward. What? Why? That's what I want you to think about. While you think about it, I want to show you one other example. Let's see if this works here. I got a piece of paper right here. If I take this piece of paper and I blow over the top of it, watch what happens to the piece of paper. Whoa, it flows. As I blow on top of the paper is actually lifted up. Wow, that's pretty neat, right? I thought it was cool. Why is that? How does that work? Same thing as what happens with the tarp here. How does this occur? Well, it's about Bernoullis principle, right? If we look at Bernoullis equation here, what I'm doing is I'm increasing the speed of the fluid on top, or when the truck is moving, the fluid on top is moving faster, right? So as speed increases, in order for the total energy per unit volume to stay the same, something else has to change. And what changes in this case, since the elevation's not moving of the air, the pressure will actually go down as the speed goes up. So when I'm blowing over my piece of paper here, as I blow over the top, I make the air move faster on top, dropping the pressure, and so the air pressure in the room actually pushes the paper up like this. So I blow over it, dropping the pressure, and it lifts as a result. Really cool stuff, right? Another cool example of the same idea is airplanes. How do airplanes work? Well, there's a lot of complexities to them, but one simplified model to understand the basics of how airplanes are able to generate lift is to understand that air moving on top of the airplane wing moves faster than air underneath because of the shape of the wing. And so since it's moving faster, the pressure on top is lower than the pressure on bottom, and therefore you get an upward lift force. So you get that faster air moving on top, slower air on the bottom, and there's a general change in pressure, which gives rise to a net force pushing upward on the airplane wing. Same thing is actually true with throwing a curveball, believe it or not, in baseball. So if you have a normal throw where there's no spin to the ball, you get even pressure on the top and the bottom of your baseball. But if you cause it to rotate, the rotation of the ball will cause air on top to travel a greater distance, therefore moving faster than the air on the bottom, which gives rise to a pressure difference between the two sides of the ball. So you have lower pressure on top, higher pressure on bottom, giving rise to a pressure difference, which results in a net force that will deflect the ball to the side. Keeping in mind this is a top-down picture. So you have a spinning ball rotating from your curve, and it will be deflected towards that higher speed side because it's lower pressure. Water towers work under the same principle. Again, thinking about conservation of energy per unit volume. In a water tower, up here at the top, you have a lot of gravitational potential energy. As you move down the pipe, that gravitational potential energy turns into pressure potential energy. And then when you turn on your faucet, it comes rushing out because that pressure turns into kinetic energy. So the last thing I want to introduce is what's known as Poisson's law. I believe that's how you pronounce this kind of unique French name. But Poisson came up with a way of how we quantify the rate at which water moves when you do not have all these ideal situations going on. So Bernoullis principle helps us understand when we have ideal flow and no viscosity, no friction inside the fluid. Poisson's law tells us what our flow rate's going to be like if we do have viscosity, causing our fluid to flow slower with length of our pipe. And so here's Poisson's law. Q is the volumetric flow rate. R is the radius of your pipe. P is the change in pressure from one end to the other. So like I like to think of Poisson's law with a garden hose. If I have a really long garden hose, it's actually going to come out slower at the end than at the beginning because of friction within that hose. So P1 would be atmospheric pressure where it comes out. P2 would be the pressure of my water in my hose bib pushing the water out, okay? Viscosity is the viscosity of your fluid, so that'd be for water, and then L is the length of your hose. So since you're dividing by L, the longer your length, the more your flow rate's going to be decreased as a result of that additional length. So I'm actually in the process of trying to put in a sprinkler system in my yard. And in the process of getting it set up, I decided, because I had so far to run my water line to get to my sprinkler system, I decided to use 3/4 inch PVC instead of 1/2 inch PVC in order to increase my radius and therefore try to have a higher flow rate of water coming out of my sprinklers to make sure they're able to shoot as far as they need to cover all my grass. So here's a cool example that we can use Poisson's law to solve. So here's a syringe. My mom growing up was a nurse, and so I used to jokingly say she shot people for a living because she would give immunization. She actually shot me 3 times when I was a kid, hepatitis B. Anyway, so here's a syringe. Let's imagine that it's my mom shooting me with this syringe, all right? So inside my body, there's some pressure, P1. P2 is the pressure at the beginning of the needle. Here's the length of the needle. And here's the area, cross-sectional area of the plunger, and F is the force that my mom's applying. So there's a fluid inside of here. Let's say it has a viscosity of 1.5 times 10 to the negative third Pascal seconds. And the internal radius of my needle, it's a thin needle, so it's only 4 times 10 to the negative fourth meters. That's the radius. Makes sense, it should be small. So let's say that the gauge pressure in my vein, again, remember gauge pressure is the difference between the pressure inside and atmospheric. So the gauge pressure in my arm is 1900 pascals. All right? What force must be applied to this plunger to make sure that the fluid inside of here, which has a total volume of 1 times 10 to the negative 6 cubic meters, can be injected in just 3 seconds? Cool, boy howdy, right? Pause it, try this one out, and then we'll walk through it together. So first of all, we want to find the force, right? Force is pressure times area, right? Since pressure is force over area. So if we want to find the force, we need to know the pressure required at the end of the plunger, right? So we know the area, but we need the pressure. So Poisson's law will enable us to determine the pressure difference, right? So P2, the pressure at the front of the needle, minus P1, the pressure at the delivery side of the needle, that pressure difference is going to be equal to the rest of Poisson's equation. So I just solved Poisson's equation, so it's going to be 8 times viscosity times length times the volumetric flow rate. Now what's the volumetric flow rate? Well, that's volume per unit time. So we take our volume and divide it by our 3 seconds, and then divide it by 4 times the radius to the 4, or excuse me, pi times the radius to the 4th power. So the pressure difference required to generate this flow rate through the needle is going to be 1200 pascals. But that's the pressure above the pressure in my arm. So then we need to then figure out the actual pressure. Since the gauge pressure in my arm is 1900 pascals, we have to add that to the pressure difference we just solved for, and so we get P2 should be 3,100 pascals. Now, some of you might want to add atmospheric pressure to this, right? Since there's only gauge pressure. But atmospheric pressure is already pushing on this end of the plunger, right? So the force that my mom needs to apply is just above atmospheric. So that's why you just use the 3,100 pascals. Otherwise, my mom would have to be like super strong in order to push it as hard as she would need to. Now with that pressure, we just plug it into force equals pressure times area. And so my mom only needs to apply 0.25 newtons worth of force in order to inject me with this medicine. Pretty good example problem, I think. Anyway, that actually wraps up chapter 14, which wraps up the entirety of the first semester of physics information. So I hope you guys enjoyed it, and I hope you have a box-worthy day and crush the final exam. Go team.